we're looking at matrix multiplication. The idea of not just doing things with rows, individual equations, but doing things with whole systems of equations, okay? So let's see if we can do just a really simple one and have a go at getting the answer, okay? So those of you who were here on Wednesday, I'm going to look to you to help me walk through this. And those of you who weren't here on Wednesday, you'll need to pay pretty close attention to see what exactly is going to come out of this. Okay. So we'll do a nice simple one. Let's do a 2 by 2 times another 2 by 2. Okay. Let's do some simple numbers like this. That will do. Okay. That's the same number. Let's try something else. We'll switch that around. All right, so how do we multiply these things? Who knows where to start? Yep.
Row by column.
Fantastic. So I might even, just as a mental cue, a visual cue, I'm going to write that down, right? The order that we multiply things by matters here, right? So matrix multiplication is not usually commutative. We can't usually switch around, okay? So we'll do rows by columns. Here is a row. And here is the corresponding column that we're going to begin with, okay? So, I will draw up my new matrix that I'm going to get. By the way, think carefully, what will the dimensions of my new matrix be?
2 by 2.
It's going to be 2 by 2. This is kind of an easy one. When you've got square matrices, it's really simple. But in case you couldn't remember, you take the dimensions of each one, row by column, 2 by 2, row by column, 2 by 2, right? And in order to make sure the matrices can multiply, what quality do I need to have? Because they can't, oh yeah, come on.
The middle numbers need to be same.
Fantastic. The columns of this one have to match to the rows of this one. And then the result will be the rows of this one and the columns of this one. Hence, 2 by 2, okay? So I'll draw that up here. I'm making it a bit wider so I can put my calculations in, okay? So we'll match up now. 1 by 4. Plus, and then I go forward, 2 by 2. Make sense? So there's my first one. Now where do I go? What's my next step? Yeah, I want to move from left to right, okay? This can't move any further to the right. It must be this one that hops over, okay? So I'm again going to do 1 and 2 times 1 and 1. Does that make sense? 1 by 1, 1 by 2. Cool, done my first row, okay? So I've done this row, now I move down, which means this is going to move down. I'll have my 0 and my 3, and I'm going to do the columns again. Okay. So, help me out, what do I write? It'll be 0 times 4, plus 3 times 2, good. And then again, 0 times 1, which is 0, plus 3 times 1. Cool. And now I can evaluate them all, yeah? Okay, up in the corner.
8. 5 to 8.
plus. 4 plus 4, okay. 1 plus 2, which is 3. That's 6. And 3. There you go. And there's our product, okay. Just to remind you, right? See each of these numbers here? What's that called? Each one of them. We've got 4. What are they called? They're called dot products. Very good. Dot product here. This is the cross product over here. Okay. Any questions? Yep.
If you had 3 by 2 and 2 by 3, it would be a 3 by 3, right?
That's exactly right.
Okay.
So rows and columns match, all good. And what you end up with is a 3 by 3. Perfect. All right, excellent. So I know that's a sort of really quick crash course version for the people who weren't here on Wednesday, but that's okay. Now, there's matrix multiplication. Now, what do you think would be the most common sense thing to do after matrix multiplication? You kind of, well now, matrix addition, I think we've done matrix addition, haven't we, right? Now, I think a natural next step would be matrix division, right? But, now I know he had a good week last week, and this is not his fault. Shh. The funny thing is, there is actually no such operation as matrix division. Now you might want to ask the question, why? However, we can still do it. I'll show you how. Right? let's just think about how multiplication and division relate at the moment. I say something like this, 4 by 5 equals 20, okay? Can you write for me what would be an equivalent statement for this that would involve division instead of multiplication? Can someone give me an example? Yeah.
The same number.
Yeah, same numbers.
20 divided by 4 equals 5.
Perfect. Okay, there you go. So what I've got here is multiplication and an equivalent division statement, right? What this really means, though, is that division is a kind of multiplication, isn't it? If I were to write this like so, right? This is just multiplication, but it's in reverse, right? So what should I multiply by to make this correct? A quarter, right? A quarter. So here's the idea. Division is just an inverse operation of multiplication, right? So to divide by something is the same as multiplying by its inverse. Does that make sense? That makes sense, okay. Now you can do the same, you can apply the same logic, right, with addition and subtraction, right? For example, 20 minus 7, okay? What is subtraction? Subtraction is just, well, it's just like this relationship, isn't it? It's addition in reverse, okay? So this is 13, but how would you write that as addition? What would you add to 20 in order to get 13? Negative 7, right? Okay, so far so good, right? So therefore, we want to do like matrix division, right? What we should really have is, well, matrix multiplication, but multiplying by, and here's our subheading for today. I'm going to run off this. Multiplying by the inverse of a matrix. Okay? So just like to divide by 4 is multiplying by the inverse of 4, to subtract 7 is to add the inverse of 7, right? What we need to do is work out, well, okay, what's the inverse of a matrix? If you multiply by that, that's what division is. All right, question for you. For its inverse for multiplication is a quarter, right? 7, its inverse for addition is negative 7. Okay. Now, where did you pull these numbers from? How did you know that that was its inverse? Apart from the fact that you know that these statements are mathematically true. Okay. What's the relationship, for instance, between 4 and a quarter? Right. I want you to think back to last lesson and look at what we looked at under the identity matrix and that kind of thing, right? How do I know that 4 and a quarter are inverses? Yeah.
4 to the power of negative 1.
Ah. 4 to the power of negative 1. Okay. I'm going to hold on to that idea. We'll return to it in a second, but I'm going to push on it a little more. Okay? Before I get your answer written, let's come back to this example. 7 and negative 7 are also inverses, but for addition. How do you know that these are inverses? This argument breaks down now. What is it about these two numbers that makes them inverses? And what is it about these two numbers that makes them inverses? Do you want to try something?
The first one, Tom, when you times it, it becomes 1. And the 1 of 2 becomes 0.
Huh. Now hold on a second. This is exactly correct mathematically, but so what? Like, why is this actually exactly what we need to write? Yeah, Brendan.
It's because one's the multiplicative and then it's 0, and the additive needs to be 0.
Good. All right. So we had two different operations, right? For multiplication, the identity is 1. You multiply by 1, doesn't change. It's identical, right? For addition, the identity is 0. You add 0, it doesn't change. It's identical, okay? So therefore, how would we go about working out or determining the inverse of a matrix? And the operation is multiplication, right? If I said, okay, let's have a matrix A, okay, and following Nikita's suggestion, right, let's make the notation for the inverse of a matrix A -1, right? By the way, this is not the only other kind of notation where we have inverses that follows the same convention. What's the other one? Think, you know this, we looked at the multiplicative inverse gives you a -1. The matrix inverse will put -1. We've been doing some trig, haven't we? Right? And if you have something like sine, then we have sine with a -1. And we're like, when you get introduced to this, we make a big deal and we say that's not 1 over sine. It's not 1 over sine, right? It's not like this. It's the inverse of sine.
Isn't that
Right.
limit the domain?
Yeah, you're starting to answer another question, but yes, kind of. Okay, but the point is that this -1, right? It kind of means just undo it. Have the inverse. That's what inverses do, right? Okay, so what have I got here? I want to end up with. I'm not going to end up with 1. I'm not going to end up with 0. What should I end up with when I put these together? Well, the identity for multiplication is 1. The identity for addition is 0. The identity for matrices is, well, do you remember what this looked like?
Identity.
This is the identity matrix. Right? And I shouldn't say the identity matrix. I should say this is an identity matrix because there are smaller ones. This is the smaller one. It's a bit boring, right? And then there are bigger ones, right? Which would have 1, 1, 1, or however many number of dimensions.